class. I was just like, oh, I'll just watch the video.
I've been watching all those to catch up from those classes I made.
Yeah.
And whoever asked when we're actually going to use the trig substitution in real life,
Yeah.
they're my hero.
Yeah. Yeah, that is a pretty common thing. Like a lot of this stuff, when will we ever use it? It's a legitimate question for most of us is probably never. But for some of you, probably will use it. Let's hold off on homework questions until we start talking about the second exam. So we're gonna finish 9-1 and then 9-3, and then talk about the exam. We had I think we had these two problems here left in 9-1 where we're solving initial value problems. So the idea here is we're given a y prime or a y double prime to integrate until we obtain the solution y of t or y of x or whatever it is, using the initial condition to figure out the constants along the way. So we've seen something like y prime, that's almost equivalent problem of, hey, here's the acceleration, find the velocity, and then second derivative, very similar process of what we're doing. So we're going to say that y of t is the antiderivative of y prime. And so antiderivative of sine t plus cosine of 2t with respect to t will give us a constant, and then we'll use our initial condition. This is our initial condition, of course. Initial condition, abbreviate that. Okay. So we have antiderivative of sine plus antiderivative of cosine of 2t. We have sine 2t over 2 or times a half, however you like to write that, plus a constant for y of t. So then we know the initial condition. T is 0, y is 4. So we have y of 4. Sorry, y of 0 rather, y of t equals 4. So our plugging in 0 in for our t gives us a value of 4. We're running out of space. So we got a negative 1. We've got a 0. So negative 1 plus c is equal to 4, which means c has to be 3. Oh, 5, yep. Oh man, we're in trouble. C equals 5. And then we plug that back into y of t to have the specific solution. Remember, the general solutions involve just unknown constants. Specific solutions have us solving for those constants. I'll just write it here. Just run out of space. As the specific solution. Yeah, negative cosine t. Okay. Does anyone have any questions on that? I hope that's nothing outside of what you've seen before. Okay, and then the example 7, we just have a second derivative. So notice we're given two sets of initial conditions here. Because we'll get a constant with our first integration, and then we'll get a constant with the second integration. So we have those two initial conditions. to find that both of those constants rather. So we're going to integrate u double prime with respect to x to get u prime of x. So what is the antiderivative of 4e to the 2x? 2e to the 2x, or 4e to the 2x over 2. Antiderivative of 8e to the negative 2x.
Positive 4e.
Yeah, 4 plus, so we have plus 4 e to the negative 2x plus c. So this is, you know, obviously this is where it's important to remember your constant of integration, right? I know some of us are in the habit of forgetting that sometimes, but it's absolutely essential that we don't forget it here. There's no way to find the specific solutions if we don't. So we'll have, this is our first derivative, u prime of t. And then we're going to use the initial condition, u prime of 0 equals 3. Figure out that c. Oops. I'll just do this. U prime of 0. So then that tells us that 2 plus 4 plus c has to be 3, which means we've got c being negative 3. Okay. So we figure out the specific u prime first before moving on to figure out what u is. So we have u prime as 2e to the 2x plus 4e to the negative 2x minus 3. So then we'll integrate that once again to get u of x. So u of x, antiderivative of u prime, which gives us e to the 2x minus 2e to the negative 2x minus 3x plus another constant. And you know, let's call that constant 1 since we called the one above it c, just to be technical. And that's u of x. So again, second initial condition comes in to solve for c. U of 0 equals 1. All right, so then what do we get? 1 minus 2 plus C1 is equal to 1. So we have minus 1 plus C1. So C1 has to equal 2. Okay, but all right. So now we have u of x, which is what we're after. We're after solutions to differential equations are the functions themselves. So the u of x is our solution that we're after. And in general, differential equations involve a lot of different strategies to solve. Some use series, which we haven't talked about. A lot of them use integration. Some of them you have to solve like systems of equations. Just varying types of techniques for these things. It's kind of like integration. It's not an easy process, but in theory, you can always check your work. Right, so solving differential equations in general isn't an easy task, but we could always solve our work, especially something like as straightforward as this. Just find the second derivative, should equal what was given to us. Time permitting, it's a reasonable thing to do just to check. Because there might be you might have made a mistake, missed a sign somewhere, so that's a viable option with these. All right, and so that's 9.1. It's a very basic introduction. Really, more than likely, nothing you saw outside of a Calc 1 setting. Okay.
We have that view in 40 over S.
Yeah. I wish. It'd be easy to grade
I
too.
mean, it's leading us forward.
You're right. And this final note is sort of technical, so I just put it there if you're interested in it. We definitely don't have the means to address existence and uniqueness for differential equations, but it's there if you're interested. Okay, so then moving into 9.3, the particular type of differential equation we're looking at is separable. Meaning we could separate variables, one variable on one side of the equation, other one on the other side, and we can integrate that. So there's the types of solutions we're after. We'll see there's implicit solutions where we have, like x squared plus y squared equals to 1. It's implicit what y as a function of x would be. It's not explicitly told to you. And then we can have explicit solutions where we know exactly what the function we're after looks like. And those will be stated in the instructions. But the method of solution, they have the most general first order differential equation. And remember, first order, it just means the highest derivative showing up is the first derivative. So we've got some function of t and y. It may involve the independent variable and an unknown function. So what we're looking at here with a change of variables, we're looking at g of y times y prime of t equals h of t. So, it may not look separable as that is like, how is that separable, or how does that allow us to integrate both sides? Because we see one function is a function of t, but we have this other function that's a function of y, g of y. So the idea is sort of explained here. If we view this y prime of t, if we view y prime of t as dy over dt instead of just y prime, then what we're looking at is a function of y times dy dt equals to some function of t, let's say. So then when we integrate both sides, we integrate with respect to the same variable. We're not going to integrate one side with respect to y and the other side with respect to t, because then that disturbs the equation, right? It disturbs the balance. But if we then say, all right, well, I'm going to integrate both sides of this with respect to t. All right, I ran out of space. Then on the left-hand side particularly, we see that the dt's just divide away, and on the left-hand side, we just have a function of y with respect to y. On the left, we have a function of t with respect to t, because again, on the left-hand side, the dt's divide out. Okay. So that's kind of what we see here in this step. Because y prime of t times dt, we're integrating with respect to t on both sides of the equation. The y prime of t dt is just dy from what we set up there. Because y prime is dy over dt times dt. Again, we'll just write that here. This is dy over dt times that dt. So that's just dy. And so that's how we end up with a separation of variables. One variable y on one side, the other variable t on the other side. Does that make sense? Do y'all have any questions on that? Okay. So the idea of the separation of variables, again, leads us to this process of antiderivatives or integration. In these problems, you'll see varying notation, but the y prime of t, some other ones, y prime of x, you might see y prime of s. So there's varying notations that we might see. Again, the independent variable t here, x here, s here. The other thing is, maybe I want to mention this, maybe I don't. Okay. So, a very generic statement here that's kind of hard to make sense of. So we'll just go ahead and look at specific examples to see that separation in action. So find the general solution, express the solution explicitly, which means we want it as y equals. Express it explicitly as a function of the independent variable here is x. So we do have a y prime, but the right-hand side is the function itself times x squared plus 1. So the equation is, what function can we take the derivative of? So it's that function times x squared plus 1 is what that's asking us to find. So before we integrate, we want the y on the other side with the y prime. Remember, y is essentially it's a function of x, but in order to separate, we need to divide both sides of the equation by y. So we have y prime of x divided by y, or times 1 over y, equals to x squared plus 1. Another way to look at that, as we wrote it earlier, this is 1 over y rather, times dy over dx equals to x squared plus 1. I don't think it really matters what notation you use. Just pick one and stay consistent with it, is what I would recommend. Okay. So then we've separated our variables. Then we're going to integrate both sides with respect to x. And so again, the left-hand side simply becomes the integral of 1 over y dy is equal to the integral of x squared plus 1 dx. So naturally, not all differential equations are separable. Okay, what is the antiderivative of 1 over y? Yeah, so that's the natural log of the absolute value of y x cubed over 3 plus x. And so technically here, what's happening is the left-hand side, we get a constant over here. So we have plus this constant. And on the right side, we get another constant as well. And so we're just going to combine them as one constant. So we're gonna subtract C1 from both sides and say C2 minus C1 is just another constant. Right? So we're just going to say that's plus a constant over here. Guess I should write a little smaller. Just save some space. All right, so what we're looking at here would be sufficient, because if the instruction said, what's the implicit solution? So here it's implicit or implied what y is, but we want the explicit solution. So we need to actually solve for y. So we're just going to exponentiate both sides. E to the ln of absolute y is just e to the absolute y equals e to the x cubed over 3 plus x plus c.
Wait, does the natural log and the e cancel, so it just becomes 1?
Oh, yeah, sorry.
Oh, okay.
Yeah, e to the ln of something is just that thing. My bad, I was looking at the other side. Thank you. So absolute y is e to that power. Do we need the absolute value there? No, because e to this power, no matter what it is always positive. So is that all right if we just say that instead of writing it out? Okay. So the way that we look at this to be a little bit more conducive to the solution is we've got e to the x cubed over 3 plus x. We have that times e to the c. So e to the c is just another constant. So this, we'll just actually say that our solution is e to the x cubed over 3 plus x times this other constant. We'll just put it here. So c times e to that power is the explicit solution to that differential equation. So the derivative of that function is the same thing as that function times x squared plus 1. Is there any questions on what we've done there? All right. Then, so the main, I think the main issue of these problems is not our integration, right? It's how do we separate so that we have, particular variables on one side and the other side. Generally, that's the confusing part or the difficult part. I'll just leave that there. Okay, so if we have u prime of x in example 2 equals to e to the 2x minus u, how would we go about separating that, if we can even separate it?
Separate e to u.
E to the, so how would we write this? We would say u prime of x is equal to, what would we write?
E to the 2x minus e to the u.
No, it's
It's
times
divided by
negative
Oh,
e
times.
times negative.
Yeah, So we want to split that up. It's e to the 2x times e to the negative u. Or it's e to the 2x over e to the u as u prime. So then we can separate that just by multiplying through the equation by e to the u. So we have e to the u times u prime is equal to e to the 2x. So now that's separated. And so if we integrate now both sides with respect to x, again, what would happen to what would happen to u prime of x dx? What does that turn into? Du. So remember u prime, just think of it, if you need to, as the derivative du over dx times another dx just gives us the integral of e to the u du, and here stays the same. Everybody all right with that? Questions at this point? Okay, so e to the u, left-hand side, 1/2 e to the 2x. Combining our constants on this side is 1. Is sufficient for an implicit solution. For explicit solution, we want to actually solve for u. So let's just all right, so what is u equal to?
2x over 2.
ln of, say it again, sorry.
E to the 2x over 2.
Plus c.
C.
Take the c out. Becomes a constant, and it's c.
So taking the ln of that to solve for u.
You take the c out. Like,
No, we couldn't, so we can't take the c out of the log because there's not a property for the log of a plus b.
Oh.
If that were times, then yeah.
Times, then you separate it as plus.
Yeah, we could just call it another constant. So that's it. I mean, if you, in reality, it's u of x, but I hope that's clear. It's a function of x. That's it. That's our explicit solution.
So if it asks for the explicit solution, and you said u equals,
Mhm.
would it be wrong?
No.
No.
Yeah, so like u equals, it's, again, it's implied that u is a function of x. It's no different than writing y equals to e to the x. You know, it's really y of x or f of x. It doesn't matter. This is a minor technicality. Okay. Any other questions on that? Yeah.
If you put the C on the outside of the natural.
Could we?
Yeah.
We couldn't actually put it on the outside. So it has to be there inside with the natural log.
Why is that?
Just because of the nature of how our antiderivative unfolded, we had a constant over here that we put over here, so we just had that constant there with the exponential. And so that whole, if that whole thing is e to the u, when we take the natural log of both sides, you can't just take the natural log of a part of it. You have to take the natural log of the whole thing. Otherwise, you're breaking that equality.
That makes sense.
Okay, good.
You have a question?
Yeah.
So for the second part, In the red at the top.
Yeah.
Integral time, red. You said you just multiply that by, to get rid of the dx and become du, it's u prime over x over dx, right?
Yeah. So the other way to think about this is that we're looking at e to the u times u prime, which is du over dx, and then we're actually introducing that part though. Let me go over this again. We're actually just introducing integration with respect to x on both sides. So that's what we do to both sides of our equation, and the dx is just divide out. So, is that what you were
Yeah,
asking?
I just wanted to
Okay.
go over that again.
Yeah. Yep. Any other questions on that? Okay. So then, with that, we can look at also initial value problems that are separable. So here's a, it says 2 times a function times the derivative of the function is equal to 3t. What function is that? Where we know that the original function evaluated at 0 is 9. So our independent variable is t. When we say y of t is equal to 9, it's our initial condition. But it's really saying that our point in this space or in this plane is a t value and a y value. So our t value here is 0 and our y value is 9. Okay. Do we need to separate?
Nope.
No, it's actually already separated for us. So we're just going to integrate both sides with respect to t. So what does the left-hand side actually represent? The antiderivative of 2y dy. Okay, so the integral of 2y dy is equal to the integral of 3t squared dt. I'll just note again here what this is. So we have y squared. Y squared equals to t cubed plus c. Okay. From here, I guess there's a couple of options from here, but let's just go ahead and solve for y. Plus minus root of t cubed plus c. And then see if we can do a little bit better than that. Do we actually need the plus minus root? Is there anything that would tell us?
The initial value.
Right, so if we go up to the initial condition here, where t is 0 and y is 9, that initial condition tells us that we're only dealing with the positive root, right? Because the y value 9 is positive, there's no way to get that out of a negative square root. So if we go back up to the initial condition, we can say that y is just the square root of t cubed plus 3. Or t cubed plus c, rather. All right, so that's y. plugging in the initial condition again allows us to solve for c. T is 0, y is 9. So we have 9 is equal to 0 cubed plus c. So what is c? C has to be, the square root of c is 9, so c has to be 81.
So I have a question.
Sure.
So when, instead of writing it as y equals t cubed plus c all over a square root,
Mhm.
we write it as t to the 3/2 plus like a different c.
No, because could we write it as t to the 3/2 plus a different c? The answer is no, because the square root doesn't operate on like sums and differences, right? So like the square root of t cubed times c, we could call that the square root of t cubed times the square root of c. But the square root of t cubed plus c or minus c isn't the same thing as the square root of t cubed plus or minus the square root of c. And so that means that the function is the square root of t cubed plus 81. Or y of t, if you will. Any questions on that example? Okay, so I'll give example 4 a shot.
think that's. No, because the plus C is supposed to be here. The sign X. So when you
Yeah. I don't know if golf really blended like as this. So I don't know. Basically, it said that this should be written as like sine x. Which is out, which is this. Which is that's why. Because even if you so like, yeah, so it's
So, okay, so if this ended up being y0, which is -3, then the -1. Yeah, literally it said like this whole thing is like plus or minus, like this thing reset in place plus or minus C, just C. Did you read that exactly? Well, that's exactly what it was.
I had to look at that.
Oh, really? Yeah, that was brief. I don't know, I needed like so much help. I needed to like find an example or whatever, like on it.
I don't know where to go from
Dude, tricks on this here is so hard.
Any real positive way to forget like brings to power because it's sometimes here. Yeah, you can make it small, like one little sort of
I'm actually going back.
yeah, you can make it smaller and smaller.
It's like, sometimes like you has to be like,
Yeah, no, I get that.
for this one. So this is supposed to be X, right? So like, oh man, I just had it. Okay. So pi over 2 would be here. Right?
Yes.
And then
So-
here.
Yeah, exactly.
yeah. Which you can just substitute arctangent. See, like the arctangent is 1 over a, which is a base, which is 1 over 5, and then arctangent is x or u squared, which is this, or just u, yeah. Well, wait, 1 is 1 over a. It's 1 over a arctangent x.
So this is
And a is, this is a squared. A squared is the base. So if you notice, this is like a square. Like not it's a good way of catching
We're not making the Quaalude moves.
Yeah.
I found him.
I guess, yeah.
Probably from like.
Whoa.
yeah, he was in
Yeah. Yeah, that's the whole point.
Really?
It is
So not only one's like 5 days from now, it's
really just, if he throws in some of the random ones when he
Dude, yes.
were like ridiculous. There's like 10 different things you have to like know for all of it.
It's just like, yeah, so here you're supposed to use sub and then a sub and then subtract 7. I was like,
Yeah.
but if it's like a trick sub, I would probably be able to do it.
Yeah. It wanted to depend on what I was doing.
If it's just like one of the ones where it's use sub, but then you have to like find X, like
As long as you take the minus one time for number, I'm not too worried about A2. I said A3 in all reality isn't hard. A2 is I'm not too worried about A2. It's just memorize the like M and which one's odd. A4 is the only one I'm like really going to try to do the problems on because it's like that one is like don't worry if it's complicated. Some of the ones where it was like x squared times the square root of this on the bottom, if you're not, it was like,
the thing that's the one where I said like sine, cosine, or like tangent. With those, it's like you got 2 choices.
yeah.
You can tell it's
They memorize the rules.
yeah. Like I was just
It's really just A4, difficult by part.
so actually that's one where it's like
Really long.
my F4 it's like 2 things. If you like
It's not bad, it's easy.
X squared and then X plus 1 dash like that.
Yeah.
It's just like, it's just that first is like problem, so.
Just to like X plus 2.
Just gonna do a bunch of problems.
So you want to multiply by 1 over y or divide by y first?
I'm actually kind of confused.
Then integrate with respect to x. So make sure you're separating before you integrate. And so we end up with the integral again of 1 over y dy is the integral of cosine x dx. ln, so we have the ln absolute value of y is the sine of x plus c. So just be careful here when solving for y that we're raising both sides, totally both sides. So this is e to the ln of absolute y equals e to the power of sine x plus c. All right, so just be careful with that step too. Sine x plus c as the power of e. So we have this here as y. So yeah, this is a positive quantity. Okay. So from here, then most of you were plugging in the initial condition. So the y is 3 and x is 0. So we have 3 equals to e to the sine of 0 plus c. Okay. So we have e to the c is equal to 3, which means that c is the natural log of 3. You just also want to be careful where you put that back in. So some people were putting it back into the implicit solution ln absolute y, and just saying that y was sine of x plus ln 3. Right? So just be careful where you're putting that back into this one here. Putting that c back into this equation, the explicit form of that solution. So we have y e to the sine x plus ln 3, which is I mean, that's fine, I suppose. We could make it a little bit simpler, though, when you write it as e to the sine x times e to the L of 3. Which is just 3, so we have 3 e to the sine x. All right. By and large, seems like everyone's understanding what we're doing here. So does anyone have any further questions on that? Yeah. From here, how do we go from here to here? Yeah, just because the sine of 0 is 0. So what we're actually looking at over here is e to the 0 plus c. Yeah. Well, it's e to the 0 plus c, so that's just the power of c.
Yeah, because that was the issue that I had.
Okay.
Okay, it's a constant, I forgot the constant was. There, I kind of ignored it.
Okay, yeah. Yeah, so that's when, like when we're not familiar or in the habit of putting plus c with our integrals, it could come back to bite us here too. And yeah, it makes a difference where that c is at, right? That c is not another thing by itself. It is in the power of the exponential. Okay. All right, let's look at this last one. There's a couple in your homework where they want you to leave the solution in implicit form, and then they have you choose the correct graph. And you'll notice that those are technology questions because these aren't very user-friendly graphs. So you're going to want to graph these somehow, and we'll talk about how to. This one is somewhat similar to a homework problem. There's a couple of these in your homework, but it says solve the initial value problem, leave the solution in implicit form, and use the technology to plot the solution. If the solution describes more than one function, be sure to indicate which function it corresponds to. The MyMathLab will have like 3 or 4 graphs, and it'll just have pieces of the graph, and it'll say the solution is the top half of this thing, or is the bottom half of this thing, or it's both of these things. And so you'll have choices. But to kind of see how that comes about, notice in our original differential equation here, we're going to write it as u prime equals to 1 over sine u times cosine of x over 2. So our independent variable is x. The function is u. So when we were given this initial condition, it's of the form of x comma u as the point. So that's pi comma pi over 2. When x is pi, u is pi over 2. Just initially we rewrote the differential equation. So notice here that u can't be 0. So let's just make a note. We'll come back to this in a minute. U cannot be 0.
Wait, I have a question.
Yeah.
So you divided cosecant on both sides, right?
Yeah, you can divide cosecant on both sides. And then,
So isn't 1 divided by cosecant sine?
well, you would have 1 over cosecant on the left, you mean? You'd have
Yeah.
1 over sine,
Okay.
which is just sine.
Oh, okay.
Yeah. So then we're going to multiply both sides through by sine. Since u isn't 0, we're not multiplying through by 0. So we've got the sine of u times u prime of x equals to the cosine of x over 2. Then we integrate both sides. With respect to x. So we have the integral of sine u du equals to the integral of cosine of x over 2 dx. Take the antiderivative. Minus cosine u is equal to, well, we have sine of x over 2 times 2 plus our constant. So before we actually plot that's not technically the implicit solution because we need to solve for c. So we're going to go back up. We were given that x is pi, u is pi over 2. So we can solve for c that way. X is pi and u is pi over 2. Okay, so we have then negative 1 equals to c. Or sorry, 2 plus c.
Is cosine of pi over 2 0?
No, it's 1.
So yeah, I was thinking of the sign. Cosine of pi over 2 is 0. My bad. So 2 plus c equals 0. C has to be negative 2. Okay, so we want to plug that back into our implicit solution. Negative cosine u is 2 sine x over 2 minus 2. Okay. So anybody have any questions on that? That's our implicit solution. Then it asks you to graph that. It's going to ask you, My Math Lab is going to ask you to pick a graph. So we're going to look at that. Minus cosine y. So we're just going to use y instead of u, just to plot it on Desmos anyways. Maybe there's another plotter. 2 sine x over 2.
Doing plus 2 and then add 0 cosine, which is
Minus 2.
Which equals 0.
So notice our implicit solution would give us all of these. That's kind of where we then go back to the initial condition to sort of zero in or hone down which one of those we're actually dealing with. So our initial condition was pi comma pi over 2. So, you know, somewhere in here is pi, right? So we know, like, just from graphing it and the initial condition that we're only talking, at least for now, that we're only talking about this, whatever that is, elliptical type shape, right? Does that make sense? Okay, so we'll put this in our initial our notes and say based off of the graph and the initial condition, this is where we are currently. So the graph initial condition. So I don't know wherever that's at. Looks like it's 3. I don't know. Maybe pi is here, and this is pi over 2. But that's not actually that whole red thing is not actually our solution. So to help see the solution more explicitly, then we should take our implicit solution and solve for u. So, naturally, we couldn't graph these things on the exam. You could certainly get to the implicit solution, but there wouldn't be a what does the graph look like type of question following that.
Why go to the implicit solution
Do what?
when you can do it the other way?
Explicit pretty easily from there.
Yeah, so what do you mean?
Well, like even without the -2, you could have gone to the explicit and gotten it.
The graph?
Well, the solution, like being
You could get the
to C
explicit
being
value.
-2, yeah.
Right. And all of these ones where we've been separating and solving, or even in 9-1, you don't have to use the explicit solution to solve for the constant. Is that what you're referring to? We can always use the implicit solution to solve for the constant too. But so I guess I'm not. Maybe I don't understand. How would the implicit solution tell us if that's the actual graph of our
Why
solution?
would it ask for the implicit solution when we can get to the explicit?
That's what he's asking me. Why?
Oh, so why?
Why is it easier this way?
Why is the question asking us for an implicit solution when we could get to the explicit solution? Like we could explicitly solve for u in this one. Sometimes you can't solve for u, but for some like this, we certainly can solve for u. But when we notice what happens when we solve for u, what's going to be involved? If we say u equals, yeah, you're going to have an inverse cosine for that, which then gives you a further restriction of the output, right? What is the inverse cosine output? Values between where and where? 0 and pi. So like thinking of looking at the explicit solution can tell us for sure, is this whole red thing an actual solution, or is it just the top half maybe? Maybe it's just the top portion of that where our initial point lies. Okay, so just looking at this through another lens then. We'll see that it does give us a little bit more information, but it also doesn't tell us, looking at the graph anyways, doesn't tell us a certain thing either. So the explicit solution, we have cosine of u equals to -2 sine of x over 2 minus
Plus this time.
2. Oh, plus 2. Negate that. And then so that means u is the inverse cosine of that quantity.
I do believe it is -2.
Here?
He transferred over a negative 1.
Yeah, because of the negative cosine, yeah. X over 2 plus 2. So let's graph that. I mean, hopefully, we just mentioned the output of inverse cosine, so hopefully you can see how that's going to affect the graph. Okay, so we see that, if we're looking at all of them, like we're outputting 0 to pi, which is why we get those blue in the inverse cosine. But again, we know that we're dealing with this one here. Now we know explicitly we're dealing with only the top half of that round-ish thing. So we can further refine that. Granted, if we didn't have the means to solve for u here, our initial condition, and the fact that we noted earlier in the very beginning that in this differential equation u can't be 0, so that differential equation is undefined when u is equal to 0. I'm gonna start a new page just so that doesn't get too small. And so u can't be 0. So let's see what happens in our solution, because our solution doesn't indicate anything. There's nothing wrong with u being 0, except for the fact that it's tied into the differential, the derivative, where u couldn't be 0. So let's just see what happens, what we get out of this when u is 0. So we have -1 as 2 sine x over 2 minus 2. You're solving this for x. Divided by, so when does sine of x over 2 equal to a half? So that's what we get from our solution when u is 0. Pi over 3, yeah, and think about our initial portion here. We have pi over 3 here, or pi over 3. So we'd say the sine of theta equals 1/2 when theta is pi over 6, and what's after pi? Say this when okay, so the sine of pi over 6 is 1/2, and what else? 5 pi over 6. 5 pi over 6. And we're just maybe pretend that we weren't able to solve for u and see that it was the top half of that oval shape. If we go back to this graph of just our implicit solution, at this point we don't know if it's the top or the bottom, right? Or both. We can say, well, we know my initial condition is here at this point, but when u is 0, the original differential equation was undefined. That's going to give me certain values of x. So all we need to look for is from here to here. We don't need to look at other values of sine that make it equal to a half. Is that clear? We don't need to go out to any further than 5 pi over 6, and we don't need to keep going out to like negative pi over 6 and all of that stuff. Okay, so we're kind of stopping there. And so that means that x has to be what? 2 pi over 6 and 10 pi over 6. So what that means is the original differential equation, or differential equation, is undefined. At pi over 3, comma 0, x, comma u, and 5 pi over 3, comma 0. So if we say our differential equation isn't defined for those particular values, sorry, the differential equation rather is undefined at 0, at x equals to 0, but that means on our solution that it corresponds to those 2 points. So if the differential equation is undefined at 0 and our solution yields these 2 points, then at those 2 points it's also undefined, right? it's kind of the contrary or the converse of that is like, if I have a function that's undefined at like 0, and I compute the derivative, right? Can the derivative be defined at 0? No, the derivative is not defined at 0 because the original function is not defined at 0. The solution here is not defined at these 2 points because the differential equation wasn't defined at 0. It's kind of like that. I don't know if that makes sense or not. So anyways, we've got those places where the solution is undefined, and it wouldn't take much to see that it's there and there, right? So that's an x value of 0, or sorry, a u value of 0. And so actually what we would conclude is like we've got these undefined places here. So it couldn't be this whole circle or whatever that is. I don't know what to call it. It's not an ellipse, it's not a circle. But this whole thing is not the solution because it's not all connected. So that's how we would know without looking at this explicitly. Still undefined there. So that's actually our solution. This is the graph of the solution to that differential equation. Does that make sense? Does anyone have any questions? I don't know if that was fuzzy. Yeah.
Just out of sheer curiosity, arc cosine has like a domain restriction, right?
Yeah.
So why was it graphing infinitely?
So the domain restriction is from -1 to 1. But what we're seeing as a part of that blue output is the range from 0 to pi. So this is pi over 2. That's why we don't see anything above that. Like all of these things disappear because they're above pi. So it's not going to output any of that stuff.
Gotcha.
And it's actually from 0 to pi, so which is why we get the top half there, y equals 0. So anything else, anything in between the purple and green is all it's going to output. Everything else is ignored, as evidenced by the graph, the explicit solution. But yeah, in order to figure out what x has to be, we would have to say, well, if we're looking at that solution explicitly, the arc cosine can only handle inputs of -1 to +1. So we would have to set up we have to figure out an inequality. When is -2 sine of x over 2 plus 2 in between -1 and 1? And then we would see that that's valid for these x values, not these x values, and not these. So that's what that would give us.
Alright.
I have a question.
Yeah.
So if you were to look at the red function, where it just had all those weird looking rugby balls hanging out,
Yeah.
like would there be a way to like rotate like all of those, like I don't know, from like 0 to 20 on the x-axis and 0 to 20 on the y-axis? Could you like rotate all balls in that like domain around the x-axis to get some like crazy like volume or something like that? Or
Oh. Yeah, I don't know, because then you would have like things that are overlapping. If I'm following.
Density.
But if you rotate it halfway, like just pi revolution.
You get the whole line.
Wait, can you do
Yeah, so you just mean like if I took this and this, but this one and this one and this one too?
yeah,
So like this L shape of these and rotated them around the x-axis?
yeah.
I guess if this were your function though, because we don't integrate implicitly. So we would have this thing implicitly defined here and say, well, okay, whatever this is, rotated around the x-axis.
So there's no way to like integrate implicit functions?
Not easily.
Not yet.
It involved like some really fancy stuff. So then we're almost like in this setting, we're almost forced to look at it like this. What's the volume of that rotated around? And then again, we would just use symmetry here. The volume of this is twice this, and then we've got 2 or 3 or 4 of them. Just multiply that by 2 or 3 or 4. But yeah, I mean, like, this is somewhat comparable to what you see in polar coordinates. In polar coordinates, you start getting these like really funky shapes. But in polar coordinates, we really just look at derivatives and integrals, and we don't really extend that into like volumes of revolution and stuff. And in Calc 3, you'll see other coordinates. You have a spherical coordinate system and polar coordinate system. So then you do a lot of stuff in different coordinate systems. Just like polar coordinates would be like, it's easier to describe a circle in polar coordinates in terms of the radius and the angle versus x squared plus y squared equals 1. So in spherical coordinates, it's more conducive in describing spheres. And so yeah, you'll get more regular shapes in Calc 3, but especially in polar coordinates, you can get like funky like 5-petaled flowers and infinity shapes, but we don't find the volumes of those even in that setting. You can, but anyhow. Okay, so that's our explicit solution. If we had to choose, we would say it's the top half of that circle, not including those endpoints. Does that make sense? Any other questions about this? Okay, so that's 9.3. We'll take a break and then talk about our second exam. All right, so our second exam consists of 5 to 6, what I guess I'll refer to as basic antiderivative. So I guess, some of them could come from 8.3 with like the integral of secant, etc. So all those ones on the first page of 8.3, like mainly the other 4 trig functions, secant, integral of tangent, integral of cotangent, integral of cosecant. You should just know those because we've seen those come up in trig substitutions. Or know how to get them either way. Natural log of x, those kinds of things. There's really not a technique involved per se, other than just knowing what they are. There's going to be 2 integration by parts. So there's one definite and one indefinite. For those 2. And the integrals on the exam will say find the antiderivative or evaluate the integral using XYZ. So it'll specify the technique that you're supposed to use. There might be 1 or 2 where no technique is specified, but if you've done the homework and you've studied, it'll be obvious like which technique to use. So by and large, most of them will say, do this by this particular technique. There's 2 questions for trig integrals. And that was section 8.3. And those involve powers of sine and cosine. I forget if they use, which one they use, but whatever. We'll just say it's cosine to the n, sine to the n. and the powers of secant and tangent. So the examples we worked in class are really good resources for those types of problems. There's 2 trig sub questions. And that was 8.4. 2 of those. I guess there's 2 or 3 partial fraction decompositions from 8.5. One of those questions will just have you set it up, like set up what the partial fraction decomposition would look like, but you wouldn't evaluate the integral. So one question. Setting up. The partial fraction decomposition. You know, like something like, for example, like if we had 18x over x plus 1 squared times x squared plus x plus 1. You just write out what the partial fraction would look like. You don't have to solve for the coefficients or integrate anything. There's 2 improper integrals. From 8.9. And those were the ones that we had to use the limits for particular bounds. There's one problem where you have to solve the initial value problem. From 9.1. And then there's one separable solve separable differential equation. And that was from 9.3. So let me just say integration by parts, if I didn't mention, that was, integration by parts was from 8.2. Yeah.
For the 5 and 6 basic antiderivatives on 8.3, you gave an example of integral of secant x. We didn't have that one on like, the trig antiderivative.
Right. Yeah. So that was before, or sorry, that was after we had those formula. So it's like you
in the work that we did in the past.
Yeah. Yeah. The examples weren't explicit. Like they weren't typed out. I don't think they might have been. Let me go back. The 8.3. Maybe we did an 8.2.
You just referenced the front page. Oh, okay, it's on the second page. But you said the front page.
Yeah, the second page. Yeah. Yeah, those. Yeah, second page.
We're gonna have to show how to like, get there, or just know what
No, just know what they are. Yeah, you don't have to derive them. So I did have a couple of questions that was emailed to me. So one of them was evaluate the integral from negative pi over 4 pi over 4 of 10 times the square root of 1 plus cosine 4x dx.
Where's this out of?
I'm not sure. Somebody emailed me. Maybe 8-1. I think it's from 8-1 because there isn't really a particular technique that we use to integrate this. So the key to this one, like, I don't know, what if we had just an antiderivative that was the square root of 1 plus cosine of 2x instead? So I don't know, maybe something like that might look a little bit more familiar. It looks familiar? So the key to either one of these is to remember the power reduction formulas we had for sine squared and cosine squared. We wrote them like this. So just a rearrangement of both of these would tell us that 2 times sine squared or 2 times cosine squared is equal to that. So that's particularly helpful here to sort of recognize that, because we can write 1 plus cosine of 2x as 2 cosine squared. Oops, sorry. I don't want to rewrite the original. Yeah, so how do we do it when it's 4x? Yeah, so what the pattern here to go from the right-hand side, like the cosine of 2x, to the sine of 1x or the cosine of 1x, is we just take half of that argument, right? So let's just modify this a bit. That's 4x as our argument. Then our argument over here for sine squared and for cosine squared is what? Yeah, it's just 2x. It's half of that. Oops. All right, so I'll get rid of this. So that's really the observation that allows us to compute the antiderivative. And then we have the square root of 2 coming out as a constant. And then it's just cosine of 2x. So that's what we need to do there for that one. Anybody have any questions on that? I don't know that it's inherently obvious when you look at that to think of that identity. But now, hopefully that you've seen it, 1, it makes total sense, and 2, if you see one like that again, you kind of know what to do.
So we're gonna have to have those.
I would know those, yeah, they're so common. So it's 10 root 2 sine of 2x over 2, and we're evaluating that. From here to here. Okay, so I just got a little disjoint here, but the main issue was the antiderivative. So I'll just go ahead and put those back in, so we're not missing anything. All right, so that's that. Any questions on that? That's, okay. So then the other one is the integral of e to the 4x cosine 9x dx. So how do we evaluate the antiderivative for that one? Yeah, by parts. So what should our u be? So our u is cosine 9x. And dv e to the 4x dx. So, I mean, I think what makes this problem a little more tricky than the one we worked in class is for sure the 4x for e and the 9x. So you get all of these coefficients hanging out. So du is minus 9 sine x, minus 9 sine of 9x dx. And v, the antiderivative of dv, so then you got these constants like 9/4 floating around. But the original integral then is u times v. So however we want to write that, u times v. Minus the integral of v times du. So I just recommend, like I said, just put everything in as it is, u, v, du, dv, and then you work on reconciling like signs or pulling constants out if you want. So from here, we could say that this is positive 9. Now, I don't know if you want to put the 9/4 together and take that out of the integral, keeping in mind that we're going to have another integration by parts, and that thing's going to get split up into two things that are multiplied by the constant. Or do you just want to leave the constant in as part of the integration by parts? I think there's less room for error if you leave the constants in for the next choice of u and dv. But I mean, maybe we can just rewrite that a little bit and say the integral anyways. And again, your choice of where you put the 9/4 is totally up to you. Put it with the e to the x if you wanted. The idea is that we still have a comparable integral. We need to do integration by parts again. And, you know, with this type of function, you'll see that it's always a comparable integral. You've got to stop when you have the same integral from integration by parts as you did originally. So when we see another integral of e to the 4x cosine 9x times whatever constant, we're going to stop there because we have to solve for that integral. So again, I mean, I don't know, do you have a preference where the 9/4 goes? Do we want to put it with the sign or the e? Does it matter to you? Okay, so our u, we'll call then 9/4 sine of 9x. And our dv e to the 4x dx. So v then, again, antiderivative e to the 4x over 4. You know, and just be careful because you're integrating and you're differentiating as part of integration by parts. So, you know, one of the biggest mistakes is people are like doing the wrong thing to get their du's and their v's. I know it might seem like a trivial thing to some of you, but just be careful. Okay, so we have cosine of 9x here as du times 81 over 4 dx. Oh, that's together. Let's see if I can fit all this stuff in here. We're going to have this. Then plus, now that integral is turning into two separate pieces. So that's u times v again, so we have 9 over 16. How do we write it? Sine 9x e to the 4x. So there's u times v minus the integral of v du. We have 81 over 16 cosine 9x e to the 4x dx. Everybody all right with that? Any questions?
Would this be a good example of something we can see ourselves?
Sure.
I don't know if it
Could
would be
be.
like more or less
Yeah.
complicated. Like this isn't too bad, it's just a lot of
Yeah.
constants.
Yeah, not too bad. I always say if something like this came up on the exam, the constants would be a little more friendly, but yeah, certainly. So then we're just going to add that to both sides because we've got the same integral. So we want to add 81/16 of these. To both sides. Whatever, we mixed up the order, but that's fine. So we've got one of those plus 81/16 of those, which means we have 97/16 of these. Equaling, we have here 1/4 e to the 4x cosine 9x. And our 9/16 sine 9x e to the 4x. And then we just want to solve for the integral itself. So we're going to multiply through by 16 over 97. So if 16 over 4, that's going to give us 4. So let's write it like this, and then we'll split it up. 4 over 97. And we have 9 over 97. Of those. And so that's it, right? You might see this, since they're both over 97, you might see this as 4e to the 4x cosine 9x plus 9e to the 4x sine 9x all over 97. But I think that's just a technical way to represent that, really.
I don't think, when I did it in my math lab, I don't think it was that tricky.
Okay. Yeah, it shouldn't be. But someone did email me and say that they were also unsure of how the 97 was in the bottom, because apparently my math lab was representing it as this latter part. But either one is totally acceptable. Okay. So any questions on that? What other questions do y'all have?
There was one more problem, I think it was on 8.1, it was the integral of 1 minus x over 1 minus root x.
Yeah, we actually did that one in class. Where was that? So it's whatever we uploaded for that homework for 8.1. Number 6. So this is a variation, but it's 9 minus. So we factored out the 9, and then we said 1 minus x is a difference of squares as 1 minus root x, 1 plus root x, and then they divide away. So we just had to integrate this right here. Yeah, sure. Okay. What else do y'all want to look at or talk about?
Office hours tomorrow, you say 1 to 3.
Yeah.
So
Wednesday, 1 to 3. Yeah. Okay. Like that? Okay.
When I integrated, I have all the right parts except the constant.
Okay. See what happened then.
Yeah, you can go to the next slide.
Oh, that's all right. Okay. So, like when you look at that, is it automatically like a trig sub integral to you?
Yeah.
See, what we have in parentheses here, the x squared plus 144, that's an irreducible quadratic. So even if you thought like, okay, well, let's try partial fractions, you wouldn't get very far because you're not going to get too much information. We have ax plus b over the 144 plus x squared, and so rather it's ax plus b over 144 plus x squared plus cx plus d over 144 plus x squared. So you might be able to do something with that. I haven't worked it out that way, but Sometimes when you see situations like a polynomial over a polynomial, it's a toss-up as to which one's more effective or efficient, rather. Is it a trig sub or is it a partial fraction? Trig sub was very specific to the sums or differences of squares, either in radicals or as powers. So the trig subs do have their limitations, but if we're going to do trig sub, then we're going to look at I guess our method anyways was we wanted it like a square plus 1 or a square minus 1, something like that, right? So if we factor out this 144, do this over here. All that's squared from here. Just got to be careful with your constant, because what constant are we actually taking out?
44 squared.
Yeah, it's 144 squared out here. We'll just write it like this for now. Which is 144 squared x1 plus x over 12 squared. Yeah.
Can you explain why it's 144 squared?
Just because it's in with this square.
Oh,
So if we factor it out, it's still squared.
like the square root.
Yeah,
Like the square root is the thing underneath, so in this case, the square is the thing underneath.
exactly, right. So if this were like the square root of that instead of the second power, we would say what we're pulling out is 1 over the square root of 144. Yeah. Squared. All right, and so that's our sort of our pre-work. Then we use a trig substitution for x over 2. So x over 12. X over 12 would be what? What's our trig sub here? Yeah, 1 plus tangent squared. Think of that tangent theta. And this tells us x is 12 tangent theta. We've got to account for the x squared too, so it's dx is equal to 12 secant squared theta d theta, and our x squared is 12 squared tangent squared. That 1 over 144 squared integral of x squared times dx all over r1 plus tangent squared squared. Is that all right? Questions about that? Where we're at? And again, oftentimes what we saw were these integrals turn into like a sine squared or a cosine squared or the integral of secant or the integral of cotangent. So let's see what we have here. We have one of those canceling with that. We can also take the 144 and divide by 12. So 12 divided by 144, that's going to cancel. 12 is now a 1. 12 will go into that 12 times. So this is going to be 12. So our constant here is 1/12. Our top still, we have tangent squared, secant squared. And 1 plus tangent squared is secant squared. So we have secant squared squared. Okay, so then we get 1/12 tangent squared. We have secant squared over secant to the 4th, so that's over secant squared. All right, so then everybody all right with where we're at? Any questions? So how do we integrate tangent squared over secant squared? Sine squared over, change this into sine squared.
Yeah, that all together should be fine.
So we write it like that. Invert multiply, we just get sine squared.
That threw me for a loop on the homework.
Yeah. So we got 1/12 sine squared. I don't know if that shows up in the magic hexagon or the super hexagon. I don't remember. Do you remember?
Oh, yeah.
That one did specifically? Or was it tangent over secant? Either way. So here we are yet again with a sine squared integral. I mean, honestly, at this point, if you just said the integral of sine squared is 1/2 x minus sine 2x over 4, like that's totally fine to me. Like I don't need to see you write out the identity every time. We've seen it enough to where sine squared and cosine squared integrals should be just as common as like the integral of secant. But anyhow, if not, then once again we're back here. Integrating that. Which gives us this. Was this wasn't definite integral, was it?
No.
Okay, so we get constant theory of integration. And so we've got to now turn our thetas into expressions involving x. So hopefully you remember what we did with sine of 2 theta. wrote that as 2 sine theta times cosine theta, just so we have a means to convert from theta to x, not 2 theta to x. From this, well, we have x over 12 as tangent. So then the hypotenuse would be what? Yeah, so it's, you get back to the thing that you start with. Is that right? So then that allows us to convert from the theta domain to the x domain. So we got our 1 over 24 theta. Theta is the inverse tangent of x over 12 minus, our 2's cancel out, sine of theta times cosine of theta. So here's sine of theta. Times cosine of theta. Plus C1 still. Can't really do anything with that until we multiply by the 1 over 24.
That went to the over 2.
The 2 from the 2 sine, cosine cancel with the 2 right
Oh,
there.
okay.
Yeah. Okay, so I guess we would distributing this in just to clean it up. 1/24 inverse tangent of x over 12 minus, our roots go away. We have x. We have 12x over 24. So that 12 and that 24 are going to give us over 2. So we have x over 2 times this thing. The roots cancel out. And then plus some other constant, C1 times 1/24 is that. So on trig sub problems on the exam, don't leave your answer. You would get points taken off if you left your answer in terms of theta. You have to convert back to the original variable. Questions on that? Involved. But
That would be a fair question, it's hopefully less tricky.
Yeah, certainly. Yeah.
Would you lose points if you didn't get the 1 over 24?
No. Yeah, this is okay here. Just it's a little bit neater than. Yeah. Okay. Anything else y'all want to talk about? Burning desires that you need to know?
Looks like if I'm on the right track here.
Yeah, removal food like that. Yeah. And then you'll have that question. 2 x plus c.
All right. Again, just like during the exam, if you're not sure of what's asked of you, or if you should show more work, like any kind of questions like that, please ask. It's better to know than not put enough, or you know, to miss a sign on something or whatever. So just ask if you have any questions or issues with certain problems. All right. Let me know if you have any questions through email, and I'll see y'all Thursday. I'll be in my office from 1 to 3 tomorrow.